or put them in the chat. So let's get started. Who's got questions? Oh.
I had a question. Oh.
Okay.
So is the test going to include anything like we did in the lab, like the first lab and the second lab?
Not directly, no. I mean, some of the stuff we'll talk about these basic database things, like tables, rows, records. So the fact that, you've been to the lab and you've done this stuff, it'll hopefully make it stick a little better. But no, not directly. Basically, the lab is pretty much separate from the lecture. The point of the lecture is to teach you about how different organizations use data. Basically, it's sort of like a light database course, but there's a lot of general IT stuff. But the lab is pretty focused. It's going to teach you Excel. It's going to teach you Access. Going to teach you a little bit of web design, so you know what's in web pages. Okay, so one thing, all the stuff about the exam format, it's all up there on the FAQ. Okay, so I'm going to say this. I'm sharing the screen now. So here, let's go into Paint. Okay. All questions about the exam format are in the FAQ. Okay, so please do read it. If you still have questions, then ask. Okay, but the format will be 35 multiple choice questions via Blackboard. Okay, and I'll post up some screenshots eventually of how that's going to look, but it's pretty easy. Multiple choice questions via Blackboard, and you get 45 minutes from the time you start. Okay, so you can start between 10 and 10:10 a.m. or between 8 and 8:10 p.m. Okay, and then you get 45 minutes from there. An important thing, number one, once you start the exam, that's it. So if you get interrupted, your computer catches fire, whatever, okay, that's still it. Okay. Number two, the exam will automatically load at the end of 45 minutes, even if you aren't connected, right? So what it's going to do, Blackboard will take any answers you've picked, right, and basically uploaded, saved. They call it saving in Blackboard, but that basically means those, and use them. Okay? So while you're taking your exam, you can periodically save your work, and that way it'll automatically be uploaded. So even if you lose connection toward the end, yeah, your stuff will still get saved. Couple more things. Number three, you only see one question at a time. So there's a best way to go through the exam, right? Which is this. Answer the questions you know. For the ones you don't, guess, but make a note that you need to return. So you do one pass forward through the exam, and then you've answered everything you know, and you've at least answered with guesses the ones that you don't, and then go one pass backward. Okay, one pass backwards. So go back through those and take a special note. Any questions that, yeah, you didn't know what this one was, go through and backwards through that way. Okay, so that's what I'll give you as far as stuff, but you know, I was hoping this would be more about review, but if people people got other stuff, let's see. Where can I see the FAQ in Blackboard? It will be on your lecture section. So we'll take you there. Okay, so I'm going to drop out of Collaborate. It is in the lecture. Okay, because I know I sent out a notification about this. Review session. So here, FAQ, yeah, here's the review stuff. If you go to course content, if you go to extras, there it is. There's the FAQ. There's the topics of interest. And this is for the one CRN, not the cohort one. It's in the same place in the cohort section. Or at least it ought to be. Yeah, there it is. Okay, so course content extras. So you're allowed to go back. Yeah, you can go back. Some of us have Chromebook. I don't know anything about Respondus. If you can't the exam with the hardware you have, you know, I don't have a fallback option. Okay, I mean, yeah. So Jessica, we can talk about that later. I will set up a you know, a quick test, a fake exam. Like I'll set up a check with a few fake questions, so you can at least verify that, you know, it works and experience how it works. Okay. What is somebody? Okay. So just a second, I'll get you this. I believe I have it set so you will find out your score at the end. Yes. Okay. Is it true that it's open notes? Yes. Okay. So I have a bunch of stuff here. Is it true that it's open notes? Yes. The exam is open notes. Okay. The exam is open notes, but that does not mean it will be easy. Okay. Trust me. Please don't take this as a personal challenge. But yeah, it's open notes. I don't believe in making rules that I'm not prepared to enforce. Okay. And when you have 400 students all taking an exam, you know, am I really going to watch 400 students that closely? No, I'm not. So it's easier. We'll keep the exam open notes, but trust me, if you're coming into this exam cold and don't know the material well, it won't go well. Yes, there is a list of topics of interest, okay, along with the FAQ. You can look at whatever you want, okay? You ask, can you click out the PowerPoints? I would say print up the PowerPoints, but yeah, you can have a browser window open, you can have other applications open, doesn't matter. Okay, so I'm going to ask the question. I'm going to answer the question. We had one here, thin versus thick clients and applications. Okay, that's the first, you know, non-structural question, and I will answer it. Okay. Thin and thick clients, thin and thick applications. Okay. So let's move that down. So a thin client is a relatively weak machine, right? Not much in the way of storage capacity or CPU processing power, right? Processing power, things like that. Okay, can't run big applications, store the data, all that. Thick client, relatively powerful machine, can run serious applications and store lots of data. Okay, now thin versus thick, clearly these are relative terms, right? Relative between machines, relative over time. but that's what we mean. So we could give an example. A so-called dumb terminal that just displays output and accepts queries, right? It doesn't actually do any of the processing locally. It gives a mechanism like the Google interface. It gives a mechanism for you to enter the query, and then it displays the output from it. Okay, an example of a thick client, could be a typical current desktop with a multi-core CPU and 1 terabyte hard drive. I'll say that's a solid state drive. Okay, can run lots of apps. Okay, so those would be fairly fairly extreme examples. Okay, thin and thick application. Talk about those. A thin application, most of the work, the application work, happens on a different machine. Okay? A thick application, most of the work happens locally. Okay, so give an example of that. Imagine if you have some big number crunching application where you send the query and you get the results back. Okay, you maybe don't do that on your own local machine, right? Maybe the query gets sent to something like Hadoop, and it gets distributed over 10,000 different machines, and you get the results back at the end. That would be a thin application. Most of the work doesn't happen locally on your machine. It happens somewhere else. Thick application, right? Most of the work happens locally. Suppose you're running SAS, right, which is a number statistical analysis software. Suppose you're running SAS just on your machine, right? That would be an example of a thick application. Most of it's happening locally. All right, now you could still interface your machine and send the results that you get to other machines, but the work of that application is happening locally. Now, what's the practical consequence of this? Practical consequence: systems are either built around thin clients, which are cheap, running thin apps, right? Because the clients don't need the power to run them, or thick clients, expensive, running thick apps. Because if you're going to spend the money for the thick clients, well, you might as well use that power, so you're going to run the thick applications, right? It wouldn't make much sense to have really powerful servers that can handle all of this, all these computations, but then not use them because you have thick clients. Okay, so these are the two models that tend to make the most sense, and where they do and don't make sense, that's very application and system specific. Okay, hope that helps. Okay, ooh, we got a lot of stuff. Okay, back to the PowerPoint. Only have one attempt. That is correct. Data replication and decentralization. Okay, so I got a next actual question. Hold on. I know we got a lot of stuff here. Replication and decentralization. Okay. So Facebook has a basic question. Should they keep all their data in one massive data center for their entire worldwide operation? Okay. Well, the answer generally, no, they shouldn't. Okay. Reasons are, number one, response time is faster for, data centers closer to users. So, for example, if you have users in South Korea, sure, it makes sense to put a data center over there so they get, faster time. Number two, system in one location is fragile, right? For a variety of reasons, physical disasters, earthquakes, that sort of thing, fires, whatever, and cyber attacks, right? So if somebody manages to hack that one system, disables it all with a massive denial of service attack, yeah, that's going to put the whole system down for a while. What else? Easier to manage data prioritization, right? Caching, things like that. Reason is, okay, I'll do a simple example. So if you have users in California and users in, say, Japan, right? Users in California will generally want the same data throughout the day. So you can easily cache that data, right? And track its popularity over time. Likewise, users in, say, Japan will generally want the same data throughout the day. ... Okay, so same thing. You can easily cache that data, track its popularity over time. But if you mix those user pools, then what happens? Then during the day, CA users will dominate traffic, and their stuff will seem really popular. But for daytime in Japan, Japanese users will dominate traffic. Okay, so there's a lot more cyclical back and forth about what's popular. And you'll have to keep caching, recaching, uncaching data, updating all that. It's going to trend a lot differently if you mix those user pools. Okay, so those are some simple reasons. Short version is you don't want to keep all your data in one place, right? You want to replicate worldwide. I'll add replication is necessary, though, because users worldwide might want the same information. Example such as friends in other countries. Okay, even though they're in another country, if they're friends with you, they're going to be interested in seeing your pictures and whatnot. Okay, back to this. Let's see. What does it mean? Let's go. Okay, so that's that. What does it mean when something runs in parallel? Okay, running in parallel. I don't know why it popped there. Running in parallel means that you have a big process that can be split into pieces, and those pieces can be run on different machines at the same time. Okay, so for example, you send a popular search term to Google, and it returns, say, 10 billion pages. Well, doing all that processing on one machine would be really slow, right? 10 billion pages, everything that's associated with that, doing that on one machine, that's going to take a while. Instead, Google breaks up the results into segments, assigns a segment to one of, say 10,000 machines, do K, 10,000 machines, can return the results much, much faster. Okay, that's an example of doing stuff in parallel. So you have a bunch of machines, each working on a part of a problem at the same time. So the idea is basically why it's called parallel. Here's the problem, here's the results. They get to you. And then the flow, right, as it goes through, is broken up over a bunch of different machines. But when you're drawing it out, the lines are parallel, right? It gets branched out into different machines, but it's all doing part of the same stuff. Okay, so I'll complete that. There you go. That's why I say working in parallel. Caching data just means keeping stuff where it's easy to get to. Okay, so let me give you a simple example of caching. Imagine you have a system with both RAM and hard drives. Okay, fast hard drives are slow. So the efficient way to respond to user requests is put the popular data in RAM, where it can be retrieved very quickly. Put the less popular data on hard drives. Okay? So the idea is you're making the most users happy at, a reasonable cost. Okay, so this is caching. Like I said, caching putting popular data, in this case, where it's easy to access, right? Easy, fast, whatever. All right. Very good. And caching is used in all kinds of ways in different applications. It's used inside your own computers, for example. So typical CPUs will have a cache of static RAM to do certain operations blindingly fast. Okay? But only a small subset of them. Okay. All right. So cache, 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 cache. Okay. Yep. Okay, here we go. Relational versus NoSQL. Yes. Okay. So remember our basic structure, relational database systems, okay? Basically like MS Access. So what do we know? Tables are built around a fixed structure. What we mean, so every row has the same set of fields with the same format within a table, right? And this is what you do in Access. So you set up the table has so many fields. For any record in that table, the fields will all have the same format, every row will have all of them. Okay? What this does, this approach makes it very quick to look up data because number one, you know that all records have the requisite fields, right? Whatever you're looking up, if it's there, it's in for everything. They all have the requisite fields. And what else? You know exactly where to find those fields, right? Because all the fields within, for any record, the fields are going to have the same size. That is, you'll know the memory offset from the start of the record, okay? Likewise, you can even, it's easier to plan around capacity because you know exactly how many records can be stored on a piece of hardware, okay? So it has some nice things, right? That structure makes it easier to do certain things. The last one, queries across tables are, well, what I used to say when I would lecture, I'd say queries across tables are quick and easy, like your best friend's sister. But yeah, I don't say that anymore, but that's what I used to say. Are still, they're quick and easy because you know the fields are there. Okay. Now, typically with SQL systems, it relaxes some of these constraints, but you miss out on some of the capabilities. Problem number one with relational databases. Number one, a large-scale relational database is probably going to be difficult difficult change, right? Because any change to the fields will require recalibrating the system, right? So for example, you might say, yeah, I'd like to make one field larger, but in order to do that, that's going to mean that you have a whole bunch of records that expand in size, and you might need some extra hardware to manage all that. Okay, so recalibrating the system like that is going to be a serious thing. And then on top of that, you have to arrange the data in a way that's going to be friendly for performance. So for example, imagine if you used to have like 6 machines that were storing your cache data. Well, when you expand some of those fields, now you need 8 or 10 machines to cache that data. So it's not that you can just easily change something and your system will work exactly the same. There can be reverberations throughout your system. You change one thing and a whole bunch of other things are going to have to change. Number two, again, a large-scale relational database is going to have difficulty running some multi-table queries because the data will be on different machines. Okay, so that means if all the data is in RAM, then all these cross checks between trying to figure out which records match with which table, all that can happen super fast. But if the data is on different machines, then that kind of cross-checking back and forth is potentially going to be very, very, very slow because all the communications, instead of happening, in microseconds or nanoseconds because it's in RAM, it's going to instead be happening at milliseconds, right? 1,000 to 1,000,000 times slower because it's happening at network traffic speeds. Okay, so those are the two basic problems there with relational databases. Now, with a NoSQL database, get rid of that. First of all, okay, so NoSQL databases basically relax some of the relational database constraints, but lack certain capabilities, right? The reason why relational databases are constrained is so that they can work well for the problems that they're designed for. You need the right tool for the right job. Number two, there are many different NoSQL models. Okay, so there's not relational databases. In a sense, they're basically all the same, right? Pose that fixed structure. But you could have different NoSQL models that relax different aspects of the relational database model. Okay, so there are many different ones. So it doesn't make sense to talk about NoSQL as just a monolithic concept. But a typical one, like we have in the slides, would be a key value store, right? So, or KV store. And in a key value store, instead of a fixed structure for the table, instead you just have a key to uniquely identify each record, but the data for that record could have a unique format, right? There's no guarantee that any records in the key value store are going to have the same format as any other records. It doesn't impose that requirement. So the good thing is you can pack in data very tightly, right? Basically, as soon as one record ends, you can start storing the next one. Can't do that in relational databases because you have fixed size fields. Okay, so even if what am I saying? So, for example, if the field size is 1 MB and your data is only 100 kilobytes, well, you've got 900 kilobytes of empty space in that record. Okay, so that's one nice thing about a key value store. You can pack in data tightly. That's a nice thing for something like Facebook that has to store exabytes of photo data. Downside, number two, right? Downside. Oh, I'll add in another upside. Data structures are very flexible. Okay, since you already don't have a structure requirement, you don't need new records to follow it. And this is good, for example, like Amazon's S3 system, okay, for what's called simple storage, allows many different end users to store data batches with unique formats. For example, you have one retail operation that has a set of quarterly data. They're going to have one format. You have some other, I don't know, maybe a customer relationship management application. They're storing an entirely different batch of data. So within that S3 system, because it's a key value store, every individual user can keep their own data however they like. Okay, so that's a nice thing. But the downside, multi-table queries are really slow because you have to dig around. I guess I got to expand this a little bit before I hit that problem. Are really slow because you have to dig into each record to find if a field exists and where it's located, right? So anytime you want to do a multi-table query, basically you have to comb all the way through every record. You don't automatically know it's there, and if it's there, you don't know where to find it. So for each record, you have to comb through like some kind of header list of all the fields that are in there and see if it's there. And if you have a lot of stuff to look through, that can take a long time. Okay? Can be very slow on large systems. Okay, so that's basically the kind of trade-off that's fairly typical. But again, there are many different NoSQL models, but the one we got a little bit in detail in class was the concept of the key value store. Okay. All right. Yep. So I see some people were paying attention when I said that. That's good. Yeah, so KV pairs, that's what we went. So hopefully that's it. Yeah, if you try to retrieve photo data in Facebook and it's not anywhere there, you're going to get some kind of error. It just happens. Okay? Like, for example, you'll get some little message that says, sorry, that picture is unavailable right now. Please try again later. Or you get some error screen that we don't know what went wrong, but something did. So sorry. Yeah. Yep. Good. Any other stuff? Yeah, okay. Haystack, sure. Well, no, I'm in a holding pattern. Just trying to maintain. Yeah. How come test isn't 50 minutes? Well, I'll talk about Haystack in a moment. Test isn't 50 minutes. Test isn't 50 minutes because, number one, most people in the physical setting didn't use all 50 minutes anyway. So that's reason number one. And number two, this is open notes. Okay. And number three, none of that Scantron nonsense. Okay. But the scores were comparable, right? The score distribution was comparable. No lecture Tuesday, just the exam. Okay, so I'm going to answer this question. I'm going to roll back up here. Haystack problem. Yeah, I'll talk about stuff in a second. Hold on. Haystack problem. So around 2009, okay, Facebook had a problem. Okay, they were paying a content delivery service to deliver content to users, right? Basically, popular content delivered quickly. And this is expensive. Okay? Second thing, Facebook growing very quickly in terms of user population and data volume and the number of requests for data, right? So for example, in 2005, a photo might have typically gotten 3 views, okay? By 2009, a photo maybe typically gets 50 views. So already, any photo you post has to be delivered to a lot more people, but plus multiplied by the larger number of postings, right? So this is a big problem. And the problem is only getting worse, right? Nice problem to have, but still a problem. Soon Facebook won't be able to pay the content delivery service, content delivery network, while remaining free, right? Facebook doesn't want to charge people to use Facebook, but on the other hand, because it's free, it's getting so much volume, it's not getting enough ad revenue to be able to pay the content delivery network if things keep growing fast. So what happens? Well, Haystack happens, right? Haystack is the solution. And the short version of it, again, embedding data in the web object URLs, right, like photos, allowed faster retrieval because Facebook didn't have to check hard drives for where photos were located, where they were stored, and whether people could see them, and what else? I don't know. That's good enough for now. So that was a lot faster. Number two, Facebook encouraged users to group their photos in albums for faster retrieval, right? So because sequential data can be grabbed much faster than random data from hard drives. Okay, I'll say on hard drives. Let's stretch this out a little bit. Okay, good. So that was basically their solution. And the key takeaway from this is basically by implementing this new Haystack model, Facebook roughly tripled its photo capacity, right? Photo delivery capacity, retrieval capacity overnight. This is a huge thing, right? So, yeah, I mean, Facebook kept on getting bigger, but because Haystack let Facebook grab a lot of data faster, it let it ride out that difficult situation, and Facebook was still able to remain free. So, Facebook is gradually phasing out usage of content delivery services by outside groups. I'm not entirely sure that they phased it out entirely. I haven't checked on this in a year or two. Last I checked, they were still using it a little bit, so for very specialized cases, but it was becoming a smaller and smaller fraction of Facebook's content delivery. Okay. So yeah, last thing, since people here, an example of the kinds of questions. Sure, I'll give you a sample question. All right, then I suppose we'll call it a day. All right. So remember, typical sample question, not on my exam, right, on somebody else's exam, might be something like, what part of a computer holds, I don't know, stores data? And you might say, number one, the keyboard. Number two, the monitor. Number three, the mouse. Number four, random access memory. Or number five, none of the above, right? Very simple question. Obviously, the answer is this, okay? And sure, maybe something like that would not be an entire, I mean, this is a cheesy question, right? Maybe on a face-to-face exam, some question like this or rough equivalent would be a typical question on exam. However, my exams, you will need to know stuff in more detail. My exam, you will need to know the material better. Okay? So, questions will be more like this. Suppose you have a system that runs on hard drives. What would be the probable consequences of replacing those hard drives with solid state drives? Okay? And the answer one, you save money. Number two, the system runs slower. Number three, gets more expensive. Number 4, the system runs faster. Okay, or number 5, both 3 and 4. Okay, so this is maybe not the best structured question, but it gives you an idea of the sort of things you're going to be asked, right? And of course, solid state drives faster than hard drives, also more expensive. Last we checked, so we're going to take that as a dogma that that's still true. So the correct answer in this case would be 3 and 4. Okay, answer 5, which says 3 and 4. So that's the kind of thing. Basically, they're going to be not so much match the term to the definition. It's going to be questions like either A, you have two concepts, how are they alike, or how are they different? Or B, right, you change something, how, what will happen? Okay, a lot of the questions are going to be like that, and those are the more difficult ones. But again, it's open notes, so yeah, I don't feel bad about that. So you need to know the material well so that you can answer these quickly within the time constraints. Okay. Yep. Okay, now again, yeah, so I see somebody said faster, somebody said 3 and 4. It is true, right? Even if I'm not 100% sure. Last I checked, again, solid state drives were still generally more expensive than hard drives. That'll probably turn around any day now, right? So this would not be an example question that is likely to show up on the exam because, you know, in particular, number 3 is a bit questionable, right? Number 3 is definitely in doubt. But number 4 would certainly be true. Okay. So I hope that helps. No, can't post old tests, but just go through, study the material. You'll be okay, right? It's not that hard if you have a good handle on stuff, I promise. All right. So I'm going to end the recording. If people have any last things, I can answer them, but, you know, we're past the whatever, so we're going to stop. Oh, why would it be considered a consequence? Because that's something that's going to change, right? Solid state drives, they run faster than hard drives. So they just are, they're faster than hard drives. So if you replace ordinary hard drives with solid state drives, your system's going to run faster. Any data you pull out from the drives will be pulled out faster.